Hello, my name is Aida Sakina binti Kahirul, and I will be discussing the questions and solutions that have been designed by my group for the topic of deadlock. On my screen here, um, we are currently considering a system with 4 processes, P1, P2, P3, and P4, with 3 resources, R1, R2, and R3. The following table below indicates the maximum requirements and current allocations for these resources. Taking a look at the table shown on the screen, for R1, the maximum for P1 would be 8 and the allocation is 4. For R1 P2, the maximum is 7 and the allocation being 4. For R1 P3, the maximum is 5 and the allocation is 2. For R1 P4, the maximum is 6, the allocation is 5. Moving on to R2, the maximum for P1 is 5 and the allocation is 4. For R2P2, the maximum is 4, the allocation is 2. For R2P3, the maximum is 1, allocation 0. For R2P4, the maximum is 6, allocation 4. Moving on to R3. R3P1, maximum is 4, allocation is 3. R3P2, maximum is 3, allocation is 1. R3P3, the maximum is 5, allocation is 4. And finally, R3P4, the maximum is 2, allocation is 1. Now, if we take out the available table listed below, it states that for R1, R2, and R3 respectively, the available is 1, 4, and 2. Now, let's move on to the first question. Firstly, we need to determine the need matrix for the system. And in order to determine the need, we must take the max and subtract it by the allocation given in the table above. Now, let's say for example of P1, the maximum would be 8 and the allocation is 4, which means that we will take 8 and minus 4. Therefore, we will get 4. Now, if we take a look below, for P1, the maximum was 8 and the allocation is 4. The maximum is 8 and the allocation is 4, which means that the need for P1 is 4. If we take a look at P2, the maximum was 7 and the allocation was 4, which means that the need would be 3. For P3 in R1, the maximum was 5 and the allocation was 2, which means that the need is 3. And for P4, the maximum was 6 and the allocation was 5, which means that the need is 1. Moving on to R2, the maximum for P1 in R2 was 5 and the allocation was 3, which makes the need 2. In P2R2, the maximum was 4 and the allocation was 2, which makes the need 2. Moving on to P3R2, the maximum was 1 and the allocation was 0, which makes the need 1. Moving on to P4R2, the maximum was 6 and the allocation being 4, which means that the need is 2. Moving on to R3P1, the maximum was 4 and we subtract it by the allocation, which is 3, which makes it 1. Moving on to P2R3, the maximum was 3 and the allocation being 1, so we subtract 1, which makes it 2. Moving on to P3R3, the maximum was 5, subtracting it by 4, which is the allocation, and we get 1. Lastly, we take the maximum of P4, which is 2, and subtract it by 1, which is the allocation, and we get 1. Now, this table shows the complete calculated need for all of P1, P2, and P3 in R1, R2, and R3. Next. This question, we have to determine whether the system is in a safe condition or not. And if it is true, then we have to also provide the allocation sequence. Now, in order to determine the safety algorithm, we have to ensure that the need is less than or equal to the available given. Now, if we take a look above here, the one that I'm highlighting right now, the one that I'm highlighting right now, we'll be talking about P1. So for P1, the need for P1 is 4, 2, and 1. But then if you take a look at the above table, which is the available table, this is what all we have for the available, which is 1, 4, and 2. And if we take a look here, for P1, four is not less or equal to 1, which automatically makes the statement as false. And because it's false, we will be moving on to the next allocation of resource, which is P2. Now, if we take a look at P2, in which the need up here is 3, 2, and 2. Now, what we have to make sure is that it is less than or equal to 1 for 2. Now, 3 is not less than or equal to 1, which automatically makes this entire statement false. Now we will move on to the next set of resources, which is P3. And the need for P3 are 3, 1, 1. Now if we look here, it is not less or equal to 1, 4, and 2. Now if any of these numbers, just only one, is incorrect, that makes the entire statement false. Therefore, that is why even though for the next set of need, which is 1 is indeed less than 4, the entire statement cannot be true because 3 is not less than 1, which makes the entire set of resource incorrect, false. They are not able to execute. Moving on to P4, we see that the need for P4 is 1, 2, and 1. Now if we check with the available, 1 is indeed less than or equal to 1. 2 is less than or equal to 4, and 1 being less than or equal to 2. Now that makes it true. Now what we do is we will be updating the available, and in order to update the available, what we do is take the current available, which is 1, 4, and 2, and you add it on with the allocation for P4. So if you see here, it's 5, 4, and 1. So therefore, we will be adding 5, 4, and 1 to 1, 4, and 2, which makes it 6, 8, and 3. Now moving on, we want to repeat this process until all of P1, P2, and P3 are true. So we're going back in a circle, starting with P1 because it was false. Now we will check if P1 with 4, 2, and 1 is less than or equal to 6, 8, and 2. If we check the first number, which is 4, 4 is indeed less than 6. Now moving on to 2, 2 is less than 8. And if we check the last number, 1 is less than 2, which makes this entire statement as true. And when a statement is true, we have to constantly update the available. Now, if you remember what I had stated above, in order to calculate the available, we take the current available listed here, which is 6, 8, and 2, and then we add it by the allocation for P1, which are 4, 3, and 3. If we add that together, 6 plus 4 is 10, 8 plus 3 is 11, and 2 plus 3 is 5. That makes it our new available. Now that P1 is true, we want to move up to, now that P1 is true, we want to move up to P2, in which in the beginning it was false. Now we check it with the, P2. So P2 has a resource allocation. For P2, our current maximum is our current need for P2 is 3, 2, and 2. Now we have to check it with the current available, which is 10, 11, and 5. Now if we check here, 3 is less than 10, 2 is less than 11, and 2 is less than 5, which makes this entire statement true. Now that it's true, we have to update the available again. So we will take the current available, which is 10, 11, and 5, put it here, and add it by the resource allocation for 2, which is 4, 2, and 1. If we add 10 and 4, it makes 14. 11 and 2, making it 13. And 5 and 1, making it 6. Moving on, we will go to P3 because that is the final need for resources in which it's stated is false. So for P3, our current need is 3, 1, 1, and our current available resources are 14, 13, and 6. So checking one by one, 3 is less than 14, 1 is less than 13, and 1 is also less than 6, which makes this entire statement true. And as always, we have to update the available. So we will take 14, 13, and 6, put it here, and add it with the resource allocation for P3. Now if we take a look here, all we have to do is add 14 and 2, making 16, 13 and 0, making it 13, and 6 and 4, making it 10. Now that's available, we have all of P1, P2, and P3 as true. So now we have a safe sequence. Now, according to the order in which they had listed as true, that is our safety sequence. So starting with P4, followed by P1, P2, and finally P3. Now, from the safety algorithm that we have calculated with updating the availables, we can come to the conclusion that the system is in a safe state. Therefore, deadlock can be avoided. Moving on to question 3, if P1 requests for another instance, 1, 1, 1, can this request be granted and justify your answer? Now, in order to see if this request can be granted, there are steps to it. First, we will be doing a resource request algorithm in which we do step 1 is to check the request, whether if P1 is less than equal to the need for P1. So the requests for P1 were 1, 1, 1. Is that less than or equal to the need of P1, which is 4, 2, and 1? Now, if we check right here, 1 is less than 4, 1 is also less than 2, and 1 equals to 1, which makes it true. Since it's true, we can move on to the next step, which is to check the request of P1 with the available. Now, if we check here, the request is 1, 1, 1, and the available is 1, 4, and 2. If we can see right here, 1 is equal to 1, 1 is less than 4, and 1 is also less than 2, making the entire statement true. Now we will be doing a banker's algorithm because we passed step 1, which we have to check if the request is indeed true or not with the need. And then we also passed step 2, which we check the request for P1 with the available. Since both are true, we can now create the banker's algorithm where we have to calculate the new allocation for P1. And in order to calculate the new allocation of P1, if we take a look up here, in which for P1, the allocation is 4, 3, 4, 3, and 3. All you have to do is add it with the request, which is 111. So when we add 433 to 111, we get 544. And we have to make sure that we update the allocation table. But because we are only allocating for P1, we only have to update P1. Moving on, we have to also calculate the new need, in which we will take the last need for P1, which is 4, 2, and 1, and then you add it with the request, you subtract it with the request, which is 111. Now 421 minus 111 is 3, 1, and 0. So in our new need table, we have to update for P1 and only P1 because the request was only made for P1. Finally, we have to calculate our new available, in which our old available was 142, and we subtract it by the request, which is 111. Therefore, we have 0, 3, and 1. Now that we've managed to calculate the new allocation, the new need, and the new available, we can now check the safety algorithm of the system. And as always, the need has to be less than or equal to the available. Now the need for P1 is 310, and the available is 031. So this is false because P1 in the very beginning, it needs 3, however, the available is 0, which makes the remaining 2 not needed to be checked, and it is false. Moving on to P2, the need is 3, however, in here, it is 0. So 3 is not less than or equal to 0, which makes this statement false. Moving on to P3, just like P1 and P2, we're starting off with 3, and it is not less than or equal to 0, which makes this entire statement false. Last but not least, we go to P4, in which it needs 121, and we have an available of 031. Now 1 is not less than or equal to 0, which makes this entire statement false. So from the safety algorithm that we have seen up above, we can come to the conclusion that the additional request of 111 from P1 cannot be granted because none of the processes can execute, as you can tell by the safety algorithm here. Now, what will happen is that it'll lead to an unsafe state, and there can be a possibility of deadlock. And we want to avoid that as much as possible in order to ensure that our system is running safely in a state where there is no possibility of deadlock. And that is all from my part of the discussion for questions and answers that has been made by my group. Thank you all for listening.